Welcome to the content material for Class 25 of Engineering Statics. You should be watching this video before your 25th class. In this lesson, we will learn the definition of the center of gravity and of a centroid, and how to determine the centroid of a cross-section. Already in this class, we've discussed center of gravity when we looked at slipping and tipping problems. In that case, we were told the center of gravity. But what does that mean and how do we find it? We'll answer those questions today. The center of gravity is the point on an object where all of the object's weight could be concentrated and it would have the same external effect on the body as would the actual weight. And we can denote the center of gravity using a dot with the letter G, or we can use a circle with the black and white quadrants like this one. The location of the center of gravity is notated with the coordinates x bar and y bar. Imagine you tried to balance your pencil on your finger. The place on the pencil where it stays balanced is the center of gravity. Let's imagine that we know that the metal part of the pencil has a length of 1 centimeter and it weighs 20 millinewtons, while the wood part of the pencil has a length of 9 centimeters and weighs 100 millinewtons. And we also know that the center of gravity of each of these pieces is in the middle of their sections. We can find the center of gravity along the x-axis by taking the weighted average of the distance x and the weight w for each of these sections. So the center of gravity of the pencil x bar is equal to the sum of the moments about the origin. So x1 times weight 1 plus x2 times weight 2 divided by the total weight. If we put these numbers in, we can find that the center of gravity is located at 4.6 centimeters from the left. Notice that it is slightly to the left of the middle, which is at 5 centimeters, and that's because the metal part was somewhat denser than the wooden part. A second term we will learn is the center of mass. The center of mass is related to the center of gravity by Newton's second law, where G is the strength of the gravitational field. In this course, we assume that gravity is constant at 9.81 meters per second squared, which is a reasonable assumption on the surface of the Earth. Therefore, the center of mass and the center of gravity are the same point. The only case where that is not true is if the gravitational field is variable, which we do not encounter in this course. The third and final term that we will learn is centroid. The centroid is the weighted average of the geometry of the object. And so we can do that for a line, for a two-dimensional cross-section, or a three-dimensional body. It's the middle of the object. If the object is homogeneous, in other words, the density is constant everywhere in the object, then the centroid and the center of gravity are at the same point. However, if the object has different densities, the center of gravity and the centroid are not at the same point. For example, consider this reinforced concrete beam. This part is concrete, and these bars inside are steel, which is denser and heavier than concrete. The centroid, which only depends on the geometry, would be right here in the middle. However, like I said, these steel bars are heavier and there's more of them on the bottom. So because of that steel reinforcement, the center of gravity would be lower than the centroid. In this course, we will focus on finding the centroid. For common shapes, we can look up the centroid locations. And this includes for rectangles, triangles, circles, and quadrants of circles. So you'll want to memorize these centroid coordinates for these common shapes. Most of them are common sense. But what happens if we want to know the centroid of a cross-section that is a combination of these shapes, like this one? We call this a composite body or a composite shape. A composite body is an object made up of simpler bodies in the table that we looked at earlier. To determine the centroid of a composite body, we take the weighted average of the composite centroids. And so here is the process for determining the centroid of a composite body. First, divide the object into simpler shapes, into the composite shapes, which can include the rectangles, triangles, circles, and quadrants. This can also include cutting out empty areas or holes, such as the hole that's missing in this part, and we can consider these as negative areas. The second step is to determine the coordinates of the centroids of each individual part. To do this, you also need to establish an x and y coordinate system with an origin. Third, determine the area of each of the composite parts. And fourth, take the weighted average of the x and y centroids separately to determine the object's total centroid. Let's see what this looks like with a few examples. In this first example, we have a wooden frame, and we're asked to find the centroid of this wooden beam. So we could do this actually two different ways. The first way we can do this is by breaking up the pieces as we see them, the three pieces of wood that are attached together. So if I draw those pieces like this, I might call this one part 1, part 2, and part 3. So now that we have it separated, the next thing we want to do is to find the centroids of each of these points and their areas. And the best way to do that is with a table. So I will start with shape, I have the x bar, the y bar, and the area of each of these. So if I have shape 1, shape 2, and shape 3, and then I'll be finding the totals of them as well. So for shape 1, we can see that the centroid of shape 1 is going to be located in the middle. So the way I'm going to have this set up is with an xy coordinate system that starts here. So here's my x, here's my y, that means the origin is here. So that means for piece number 1, the centroid is here. The centroid is here, the centroid is here for parts 2 and 3. So this distance is 400 millimeters, and that's going to be right in the middle. So for shape 1, it's 200. The y bar is going to be located in the middle of this piece, and this is 200 millimeters, and this is 50. So half of 50 is 25, so it's going to be at 225 millimeters. And so to find the area, we're going to multiply 400 by 50, so that area is going to be 20,000. Okay, now we also want to find the product of x bar and the area and the product of x bar or y bar in the area. So that's simply taking the product of these two numbers. That works out to 4 million. For our next shape, shape number 2, we see this centroid here. So that x bar is 25 millimeters from the origin, and the y bar is 100 millimeters, And the area, again, is this time is 200 times 50, so that's equal to 10,000 square millimeters. Find the products. And then we move on to shape number 3. Shape number 3, the x-bar is going to be all the way over here, so this is a distance of 350, and then we go another 25, so that's 375 millimeters, and the y-bar is at 100. Find the area, same area, find the products. Now we don't need this, but we're going to add up the sum of everything in this column. So that in all of the areas together, when we do that, we find that adds up to 40,000. We're going to add all of these up. We're going to find the sum of those products. And that's 8 million. And the sum here, 6.5 million. And now we have everything we need. X bar is equal to the sum of the products divided by the sum of the areas. So the sum of the x products and the sum of the areas works out to 200 millimeters. And do the same thing for y bar. So if we want to write the answer of the centroid, we can do it like this. Now there's actually a second way we can do this, considering negative areas. So instead of thinking of it as the 3 wooden pieces, we could think of it instead as one large rectangle with a smaller rectangle cut out of it. And so this would be actually one positive area and one negative area, like this. So if we do that, it would work out like this, that we would have instead only 2 shapes, shape 1 and a negative shape 2. We follow the same procedures, find the centroids, the area, and the products. Now let's check and to see if this works out to the same answer. Now area 2, shape 2, is a negative area. So we're going to give it negative numbers for the area. Now the centroid depends on the x and y axis, but the area is negative 60,000. And so because we have 200 times negative 60,000, this product over here is going to be negative 12 million and negative 6 million. And it turns out, if we add up the totals here, we find, again, 40,000 for that area, 8 million, and 6.5 million. So we see that we can do this 2 different ways and still end up with the same answer. Let's look at one more example. So in this example, we have this shape. Again, there are multiple ways we could break this up, but the way I'll break this up is by looking at this as a square and a triangle with a rectangle cut out of the square. So I'll call this shape 1, shape 2, and shape 3. And so it's going to be equal to shape 1 plus shape 2 minus shape 3. And we're going to set up our table the same way. Put in our units. So let's look at where the origin is and the x and the y-axis. We see that it's kind of in the middle. It's already been drawn for us. So based on that, the centroid of our shape 1 for the x is negative. The width of that square is 3 feet, so in the middle of that is negative 1.5 feet from the origin, while the x is in the, or the y is in the positive direction. Find the area is 9 square feet, and then we're going to take the product. So this is negative 13.5, and this is positive 13.5. For the triangle, the centroid of a triangle is h over 3 and b over 3, so it's going to be 1/3 of those dimensions. It's 3 feet by 3 feet, so we're going to have 1 feet and 1 feet, both for the x and the y of that triangle. Find the area, 1/2 b times h, and that gives us 4.5. Take the products, easy, 4.5, 4.5. Now we need to find the centroid of that negative space, shape number 3. So for the x centroid, we have to go over 2 feet, and the width here is 1 feet, so that means it's negative 2.5. And for the y, we go up 1 feet and then up another foot, making the y centroid 2. Now the area, remember, is 1 times 2, so it's 2, but it's negative. It's a whole, so it's negative 2 feet, square feet. Then we take the product of these. So we have a negative times a negative, which is a positive, 5. And then here we have a negative 4. Finally, we add up for the totals. So 9 plus 4.5 minus 2 gives us 11.5. We add up over here, we actually get a negative 4, and over here we get positive 14. Last step. Solving, we get negative 0.348 feet for y. Solving, we get about 1.22 feet. Finally, writing our answer. The centroid of this shape is located slightly to the left of the origin and at a height of 1.22 feet. And that's how we find the centroid of composite shapes.